GNU Hurd. GNU Hurd is a collection of microkernel servers written as part of GNU for the GNU Mach microkernel. It has been under development since 1990 by the GNU Project of the Free Software Foundation, designed as a replacement for the Unix kernel and released as free software under the GNU General Public License. When the Linux kernel proved to be a viable solution, development of GNU Hurd slowed, at times alternating between stasis and renewed activity and interest. The Hurd's design consists of a set of protocols and server processes or daemons, in Unix terminology, that run on the GNU Mach microkernel. The Hurd aims to surpass the Unix kernel in functionality, security, and stability, while remaining largely compatible with it. The GNU Project chose the multiserver microkernel for the operating system, due to perceived advantages over the traditional Unix monolithic kernel architecture, a view that had been advocated by some developers in the 1980s. Name and logo. In December 1991, the primary architect of the Hurd described the name as a mutually recursive acronym. As both Hurd and Hurd are homophones of the English word herd, the full name GNU Hurd is also a play on the words herd of GNUs, reflecting how the kernel works. The logo is called the Hurd boxes, and it also reflects on architecture. The logo is a graph where nodes represent the Hurd kernel servers and directed edges are IPC messages. Development history. Richard Stallman funded the GNU Project in September 1983 with an aim to create a free GNU operating system. Initially, the components required for kernel development were written: editors, shell compiler, debugger, and so on. By 1989, the GNU GPL came into being, and the only major component missing was the kernel. Development on the Hurd began in 1990 after an abandoned kernel attempt in 1986, based on the ResearchTrix operating system developed by Professor Steve Ward and his group at MIT Laboratory for Computer Science (LCS). According to Thomas Bushnell, the initial Hurd architect, the early plan was to adapt the 4.4 BSD-like kernel, and, in hindsight, it is now perfectly obvious to me that this would have succeeded splendidly and the world would be a very different place today. In 1987, Richard Stallman proposed using the Mach microkernel developed by Richard Rashid at Carnegie Mellon University. Work on this was delayed for 3 years due to uncertainty over whether CMU would release the Mach code under a suitable license. With the release of the Linux kernel in 1991, the primary user of GNU userland components soon became operating systems based on the Linux kernel Linux distributions, prompting the coining of the term GNU/Linux. Development of the Hurd has proceeded slowly. Despite an optimistic announcement by Stallman in 2002 predicting a release of GNU/Hurd later that year, the Hurd is still not considered suitable for production environments. Development in general has not met expectations, and there are still a significant number of bugs and missing features. This has resulted in a poorer product than many, including Stallman, had expected. In 2010, after 20 years under development, Stallman said that he was not very optimistic about the GNU Hurd. It makes some progress, but to be really superior it would require solving a lot of deep problems, but added that finishing it is not crucial for the GNU system because a free kernel already existed Linux, and completing Hurd would not address the main remaining problem for a free operating system: device support. The Debian project, among others, have worked on the Hurd project to produce binary distributions of Hurd-based GNU operating systems for IBM PC-compatible systems. After years of stagnation, development picked up again in 2015 and 2016, with 4 releases during these 2 years. On August 20, 2015, amid the Google Summer of Code, it was announced that GNU Gix had been ported to GNU Hurd. Architecture. Unlike most Unix-like kernels, the Hurd uses a server-client architecture, built on a microkernel that is responsible for providing the most basic kernel services, coordinating access to the hardware, the CPU through process management and scheduling, RAM via memory management, and other various input/output devices via /or scheduling for sound, graphics, mass storage, and so on. In theory, the microkernel design would allow for all device drivers to be built as servers working in user space, but today most drivers of this kind are still contained in the GNU Mach kernel space. According to Hurd developers, the main advantage of microkernel-based design is the ability to extend the system. Developing a new module would not require in-depth knowledge of the rest of the kernel, and a bug in one module would not crash the entire system. Hurd provides a concept of translators, a framework of modules used to extend a file system functionality. From early on, the Hurd was developed to use GNU Mach as the microkernel. This was a technical decision made by Richard Stallman, who thought that would speed up the work by saving a large part of it. He has admitted that he was wrong about that. Other Unix-like systems working on the Mach microkernel include OS/1, Lite, and MK Linux. macOS and NeXT Step use hybrid kernels based on Mach. Other microkernels. From 2004 onward, various efforts were launched to port the Hurd to more modern microkernels. The L4 microkernel was the original choice in 2004, but progress slowed to a halt. Nevertheless, during 2005, Hurd developer Neil Walfield finished the initial memory management framework for the L4/Hurd port, and Marcus Brinkman ported essential parts of glib, namely getting the process startup code working, allowing programs to run, thus allowing the first user programs, trivial ones such as the Hello World program in FILESYSTEM to run. Since 2005, Brinkman and Walfield started researching Kleotos as a new kernel for Hurd. In 2006, Brinkman met with Jonathan Shapiro, primary architect of the Kleotos operating system, to aid in and discuss the use of the Kleotos kernel for GNU/Hurd. In further discussion, Hurd developers realized that Kleotos as well as other similar kernels are not suitable for Hurd. In 2007, Hurd developers Neil Walfield and Marcus Brinkman gave a critique of the Hurd architecture, known as the critique, and a proposal for how a future system may be designed, known as the position paper. In 2008, Neil Walfield began working on the Vengus microkernel as a modern native kernel for Hurd. In the meantime, others have continued working on the Mach variant of Hurd. Unix extensions. A number of traditional Unix concepts are replaced or extended in the Hurd. Under Unix, every running program has an associated user ID, which normally corresponds to the user that started the process. This ID largely dictates the actions permitted to the program. No outside process can change the user ID of a running program. A Hurd process, on the other hand, runs under a set of user IDs, which can contain multiple IDs, one or none. A sufficiently privileged process can add and remove IDs to another process. For example, there is a password server that will hand out IDs in return for a correct login password. Regarding the file system, a suitable program can be designated as a translator for a single file or a whole directory hierarchy. Every access to the translated file or files below a hierarchy in the second case is in fact handled by the program. For example, a file translator may simply redirect read and write operations to another file, like a Unix symbolic link. The effect of Unix mounting is achieved by setting up a file system translator using the setrans command. Translators can also be used to provide services to the user. For example, the FTPFS translator allows a user to encapsulate remote FTP sites within a directory. Then, standard tools such as ls, cp, and rm can be used to manipulate files on the remote system. Even more powerful translators are ones such as UnionFS, which allows a user to unify multiple directories into one, thus listing the unified directory reveals the contents of all the directories. The Hurd requires a multi-boot compliant bootloader, such as grub. Architecture of the servers. According to the Debian documentation, there are 24 servers, 18 core servers, and 6 file system servers named as follows. Core servers. Auth authentication server receives requests and passwords from programs and gives them an ID, which changes the privileges of the program. Crash server handles all fatal errors. IO translation server to JUXEC execution server translates an executable image, currently ELF and out are supported, to a runnable image in memory. FIFA translator implements name pipes. New FIFA server, an alternate server for name pipes. Firmlink, the firmlink translator, implements firmlinks halfway between a symbolic link and a hard link. FWD forward server forwards requests to other servers used by FIFA and symlink servers. HostMux host multiplexer server sock server for sockets interface helps with Unix domain socket addresses. Init server, basic system booting and configuration. Magic server signals that the name lookup must be resolved internally by a process when the result involves the process's state. Null server implements /dev/null and /dev/0. Finite server implements the pfInit protocol family. pfocal server implements Unix domain sockets. Proc process server assigns PID and manages process level actions. Symlink symbolic link translator implements symbolic links for file systems that don't support them. Turn terminal server or POSIX terminal. UserMux user multiplexer server invokes user-specific translators. File system servers. Extros, the X4 file system translator. It receives disk blocks from the microkernel and gives files and directories to the applications. iSoft's the translator for the ISO 9660 file system. Translates blocks of a CD or DVD to files and directories for the applications. NFSC network file system. UFS translator for the BSD file system of the same name, UFS. FTPFS file transfer protocol file system translator. Story or the storage translator. The servers collectively implement the POSIX API with each server implementing a port of the interface. For instance, the various file system servers each implement the file system calls. The storage server will work as a wrapping layer, similar to the block layer of Linux. The equivalent of VFS of Linux is achieved by libdisks and libpedia libraries. GNU distributions running Hurd. Hurd-based GNU distributions include Hurd B GNU/Hurd discontinued Debian GNU/Hurd Gentoo GNU Hurd discontinued GNU/Hurd Live CD discontinued GIG system under development.